So while you were reading, I brought you a little model kit, and we're going to actually build the reaction that occurs between hydrogen and oxygen to make water. So, universally, as far as model kits go, hydrogens tend to be white and oxygens tend to be red. So we need to build two H2s. So take two hydrogens and put them together. There's your first H2. And then do it again. The trick here for me is going to be not letting them roll away. Do that. And then oxygen is actually made with a double bond. So to build a double bond with these model kits, you're going to use the springs. So you're going to attach two red ones together with one spring, then take a second spring and kind of bend it around so that you make literally two bonds. So there's the O2. All right, so every table should have two H2s and an O2. If we look at what the story says here, it says energy enters the reaction and breaks two hydrogen bonds and one O2 bond. So we're going to draw here, energy enters. Now, this next step is important, and it's going to make you feel silly, but it's going to make you never, ever forget. We need to apply energy to break these. So, you have to make the noise. Okay? So there's two hydrogens. Keep making the noise. Okay. Because it's taking energy to break the bond.
Oh, two at once.
All right. Okay. Now, all that racket is what is going to make us remember that it takes energy to break bonds. You had to put energy into the process to get this done. So it says in the middle, which we have never talked about and which only exists for a tiny fraction of a second, all the bonds are broken and the parts are just atoms. So there we have a heaping pile of atoms, energy gone in to break the bonds. Now we're going to make new bonds, and it's going to make the atoms so happy to get to be part of something different and not have to lay in this jumbled heap that they're going to release energy as this happens. So build the water molecule out of your pieces. Ah, that feels so much better. Okay. And build another one. Ah, that feels so much better. Okay, so all of this making of silly sounds is going to help you remember you have to put energy into the system to break the bonds, and energy comes out of the system when we break the when we remake the bonds. So then the only question becomes, on the whole, did we have to put more energy in, or did more energy come back out? And that tells you whether the reaction is what we call endothermic or exothermic. Either we put in more energy than we released, in which case it's endothermic. I invested more than I got out. Or I got out more energy than what I put in which case it's exothermic. I invested some energy, but I got a lot more out. There are a couple of ways to represent this. This energy absorbed or released in the chemical reactions is actually a third energy count, E chem. So you could represent it with an energy bar chart where you moved energy in and out of a third account, because chemical energy is the energy stored in the bonds of substances. I find it easier to represent it with something called an energy profile curve. And here's an example of an energy profile curve for water. The energy stored in the bonds initially, when it was two H2s and an O2, so when we started out, there's some amount of energy stored in those bonds initially. We put energy into the system until we had a little pile of nothing but atoms. So that took us up this hill. We had put energy in, but none had come out. All that grunting and grumbling to get to the top of the hill is actually something called activation energy. It's the energy that has to be invested to rip everything up into little pieces so that the chemical reaction can start to occur. It happens that in the case for water, the energy that came back out again was more energy than we actually put in to get to the top of the hill. So when the energy is released, this was the sigh of relief coming back out as the new bonds formed. And on the whole, energy actually was released from the reaction. The enthalpy of reaction is the difference between where you started and where you ended. And in the case of water, more energy gets released when the new bonds form than what we had to invest to break the bonds in the first place. And so this thing is going to have a delta H that when you do energy final minus energy initial, it's going to have a negative value for delta H. We call it exothermic because energy is exiting the reaction. And if you touch it, it's going to feel hot because energy is leaving the reaction. That energy is going to be entering your hand or the atmosphere or whatever it is that happens to be touching the reaction. You could just as easily represent this with an energy flow circle if you don't need all that detail, where this represents the energy in, the energy it took to get to the top of the hill, and the purple one represents the energy out, the energy that was released when you came off the hill and went down to here. I think initially this one makes it a little more clear in terms of why some energy has to go in and some energy has to go out. Because it's easy to see an exothermic process and go, well, energy just went out. But that's not the case. The just went out thing that makes it feel hot is really some investment to get to the top of the hill and a greater return to get back to the bottom of the hill. Now we can look at a real similar situation for the opposite kind of reaction, an endothermic reaction, where you invest rather a lot of energy to break the bonds to get to the top of the hill. But when you come back down, you don't come back down as far. And so in this case, the energy we put in far exceeded the energy that came back out. So the enthalpy of reaction ends up being positive, because when you take final minus initial, it ends up being a positive value. It's endothermic because energy is entering the reaction, and it would feel cold. Because that energy entering the reaction, if you were holding this thing, the energy entering the reaction would be leaving from your hand. This is the instant cold pack that's in a first aid kit where you punch it and you shake it up and it gets cold. That's just an endothermic reaction. From an energy flow circle situation, this is where the energy in is much more than the energy out. So on the whole, it appears as if the reaction is taking in energy. There are a whole bunch of different enthalpies, but they all work the same. There's enthalpy of fusion and enthalpy of vaporization and enthalpy of sublimation, if you have something like dry ice that undergoes sublimation. There's enthalpy of reaction. They actually use the phrase enthalpy of combustion, specifically if it's a combustion reaction, but it's the same idea. And then there's enthalpy of solution, energy that's released or absorbed when a substance dissolves in water. From this point, I'm going to turn you loose to deal with things we can do with enthalpy change. And so what this is some reading, and then you're going to get to spots where it says, go find the Ed puzzle. I've loaded the Ed puzzle into today's folder on Schoology, so you're going to do the Ed puzzle, and then based on what you learned from the Ed puzzle, you'll do a practice problem. You'll watch another Ed puzzle, learn about standard enthalpy of formation, and based on the Ed puzzle, do another couple of practice problems. So kind of an interactive video lecture situation here, making use of Ed puzzle to help keep you engaged in the process. So you can disassemble your model kits and put them back in the box and return them. In fact, most of you need to do that because you're not going to be able to have your model kits on your desk and focus all at the same time. So disassemble those, put them away, and you can resume at this point things we can do with enthalpy change.